All right, welcome everyone to today's joint webinar. This is co-hosted by the ASQ Quality Management Division and the Inspection Division. Today's topic, it will be industrial metrology. So my name is Kurt. I'm the host. I'm with the Quality Management Division. And joining us today will be Charlie Turch and Brandon Hagans. There it is. There's the biography. They're both experienced application engineers at Zeiss Industrial Metrology, and they specialize in optical sensors, everything ranging from the O-Inspect multi-sensor CMM to the line scan and dot scan sensors. As application engineers, both Brandon and Charlie train customers daily on optical and tactical Zeiss coordinate measuring machines, or CMM. They are experienced CMM programmers with a wide variety of real-world applications experience in a whole host of industries such as automobile, medical, and aerospace. Now, before we begin, let me just set some ground rules for the webinar. The Q&A section, our functionality has been disabled. If you have any questions, please use the chat room. All right, that's how we're going to advance the questions, make sure that either Brandon or Charlie can see the questions. They're the engineers. They're the ones that will be responding. The plan here is to go through the presentation, which is scheduled to last approximately 30 to 44 minutes. Notice I said 44. And once that's done, we'll have a dedicated Q&A section. So that's the plan. I'm going to go ahead and mute myself, but if you could, Brandon and Charlie, take it away.
All right, thank you, Kurt.
You're welcome.
As you said, my name is Brandon Hagans. I'm an application engineer at Zeiss, specializing in our optical systems, O-Inspect, V-Scan, line scan, dot scan sensors.
Wonderful. And I'm Charlie Turch. Me and Brandon have very similar roles here at Zeiss. We do a lot of the same things daily. And I think that introduction summed it up quite well on our tasks. So we're glad to have you here. So at this point, we'll let Brandon, take it away.
All right, so before we get started, I want to go through an outline of what we're going to be discussing. So first, we're going to go through an introduction to white light confocal sensor technology. Then we're going to give some demonstrations of the Zeiss dot scan white light sensor in particular. And finally, we'll wrap up with some additional resources for you and an opportunity to ask questions. So going into a little bit more detail on that, I'm going to be taking the section on sort of the introduction. I'll be discussing the theory behind white light sensors and the technology built into the sensors that enables them to measure. And then Charlie's going to be discussing the applications and the demonstrations. So talking about the advantages of white light sensors over other types of sensors, different materials that white light sensors are well suited for, their accuracy, as well as sort of where we see the white light sensors going in the future, in particular at Zeiss. And then again, we're going to wrap up with some additional resources and an opportunity for questions. All right, so with that, let's get started with the introduction to white light sensor technology. So to start off, I want to show this video here. I think it gives a good overview on the capabilities of white light sensors, particularly the Zeiss dot scan. Oh, 1 minute. All right, some of this is in German. Zeiss is a German company, so I apologize. I'll do my best to paraphrase here. So you can see here a view of the Zeiss O-Inspect. So the Zeiss dot scan is capable of a wide variety of applications, and it's very interchangeable, customizable. So you can take it off of a CMM like the Zeiss Acura, move it to the Zeiss O-Inspect. So you can see here. Now here we're going to see a view of the Zeiss dot scan white light sensor actually measuring. So you can see we have a fourth axis. Here we have a rotary table rotating our workpiece, and the Zeiss dot scan white light sensor is measuring that workpiece as it rotates. You can see no contact is necessary. It's a non-contact sensor. So one of the great capabilities of white light sensors is the ability to measure interesting materials, such as transparent materials, as you can see here. This might give problems for other types of optical sensors, but no problem for the dot scan. You can see here in the software scanning and registering of measuring points, and it's actually measuring on both sides of the material, so you can actually do thickness measurements with white light sensors. Another capability is actually active scanning. You can see here that the sensor actually moves up and down following the contour of the workpiece as it rotates, just as a tactile stylus might do in measurement. So I like to show that video. I think it gives sort of a good overview of where we're going, a good introduction to white light sensors, but also the dot scan in particular. So to start off, let's talk about what principles sort of govern the function of sensors like this. So these sensors use white light to measure. You can see in the bottom right corner, that image there has the reference sphere used to calibrate the sensor, and then a white dot of light on top of that sphere coming from the sensor. So white light, as you can see from the image above, is really all of the colors of the rainbow combined. You can think Pink Floyd, Dark Side of the Moon here. So we have the prism that white light is going into. A prism is able to actually split the light into its component colors, red through violet. So we might have some source, some white light source, like an LED or a light bulb, and that can be split into its component colors. So what defines those colors is what's known as the wavelength. So that's the distance between one peak to the next peak in a wave of light. We're considering light to be a wave in this case. Shorter wavelengths, such as 400 nanometers, would correspond to violet, whereas longer wavelengths, such as 700 nanometers, would correspond to the red side of the spectrum. So looking at how the actual sensor would work, we have a white light source at the top here. Oops, looks like we have a glitch here. It's loading.
Yeah, sorry about that. Give me 1 second here. It's coming back up.
Okay, sorry about that. So we go to the next slide here. So we have a white light source at the top going into the sort of the tube of the sensor, and then inside the sensor itself, we have a series of stacked lenses. So what those lenses do is like what you saw with the prism on the previous slide. It will split the light into its component colors, its component wavelengths, but it will also focus that light down underneath the sensor, as you can see there. So each color of light, each wavelength of light, travels a specific distance away from the sensor, and then ends up on top of the object being measured. So the part that you're trying to measure, the light will hit that part. Now, going into a little bit more detail on that, we have another diagram here off to the right. We have the light source. We have an optical fiber that's carrying that white light into the optical probe head with a series of stacked lenses. And then we have the surface underneath being measured. So the light going through those lenses of the different colors will leave the sensor at a slightly different angle depending on what color it is. You can see here in the example, the blue light here is angled very sharply underneath the sensor, whereas red light will be sort of have a more shallow angle leaving the sensor. So the difference between where those, the blue light versus the red light is in focus, gives the working distance of the sensor, the area where it can measure. So this is what's called the focal point, the point in space where a given color of light is in focus. You can see in the example here, the green light is in focus on the top of the surface being measured. So that's the color of light that's going to be reflected back into the sensor and then into what's called a spectrometer, which we're going to talk about a little bit later. So going back to our original image here, you can see here, like I said before, the focused wavelength then reflects back up into the sensor spectrometer, which detects and processes that information. So if we take a look here, we go to the next image. We have this chart here. We have wavelength on the bottom, so the color of light, and then intensity on the y-axis of that chart. So here you can see, as in the example, we have green light reflecting back into the sensor, meaning that the sensor is able to determine how far away that surface is from the sensor based on the color of light that gets reflected back here. So something to note about these spectrometers is also that they're very precise. They have resolution down to the nanometer level. So anywhere within that range, 400 nanometers to 700 nanometers, you're able to very accurately determine the position of the surface away from the sensor. So here's a good sort of illustration of how the sensor works. You can see if the surface is farther away, it reflects red light. If it's close, it reflects purple. If it's somewhere in the middle, the surface is going to reflect green light. Now, if we're scanning across a surface, you can see here that the sensor is maintaining green light being reflected into the spectrometer the entire time as it scans across that surface. Now, if we have an actual surface is going to be flat like that. We're going to have these rough sort of peaks and valleys we're traversing. So you can see as the sensor moves across that surface, depending on how high the peak is or how deep the valley is, a different color of light will be reflected into the sensor, and we're able to get information on form deviations of that surface. So something to note here, you saw as it traveled across, it was following that nominal surface, so that the information it has on that surface, it assumes that the surface is perfectly flat and follows that surface, as you can see there. But with the Zeiss dot scan, it's actually able to actively scan, as we saw in the earlier video, and actually follow the real contour of that surface as well. So there's sort of two different scanning modes with it, but that's just an aside. So here's another video. Sorry, the links are a little finicky, I think. So this video sort of sums up the what we've discussed so far in the theory and technology. Yeah, let's maybe just try the link, Charlie.
I think we're just going to have to move past that one. It's a very similar video to the last video that you saw that kind of highlighted the
sorry about that, everyone.
The sensor moves. But.
All right, I can sort of discuss what it shows to some degree. So it goes through similar things like you saw in the first video, talking about sort of the speed with which the sensor can measure as well, and you can see even in the image there the different heights of the focal points of the different colors and how that works. It also discusses additional things that Charlie's going to be going into more detail on, such as thickness measurements, fast measurements and different materials that the sensor can measure as well. But I think I will leave that to Charlie if you'd like to take over there.
Yeah, and we'll be highlighting a lot of those things here coming up, so don't worry. All right. So what we'll be really talking about next is kind of the capabilities of the sensor. You now know kind of how it functions, but where can we use it and what good can it provide us in our everyday workplace? And what we'll be doing is kind of comparing it to old traditional ways of scanning. And when we say that, for those of you that might not be as familiar with industrial metrology, kind of the old way of scanning was always taking tactile points, excuse me, with like a touch probe, where you actually have a ruby coming down and touching a part in different various locations, whether you're taking 10 points on the top of it or scanning thousands of points kind of all over. And that's where really this sensor takes up. It can do a lot of those same things that a tactile, an older traditional style of sensor could do, but it really kind of takes it to the next level. For instance, very increased scanning capabilities with a sensor like a white light sensor. In this case, we'll be highlighting a lot of the dot scan because that's our white light sensor, so we're very familiar with it. When I say increased scanning, I mean taking many, many points. Traditional ways, sometimes you'd maybe take 5, 10 points on a part and then you'd call it good. Well, nowadays you can get a lot more, but with a white light sensor like this, you can take thousands of points in a second. So you can imagine you can take many, many points with a scanning sensor like this, and you can do it at very high speeds. So instead of kind of being the bottleneck in the manufacturing process inspection, obviously you don't want to be the bottleneck, so we want to be able to inspect parts as fast as possible and get them out the door as fast as possible. So I'll show you guys a little video here. Oh. All right, let's see. No. And maybe the video isn't going to want to go through here. Let me try it here. All right, let's try it again. Yeah, it doesn't. Okay. Well, basically it's a video, and we'll make sure we make this PowerPoint available for all you if you want to come back and watch the video, but it's a video showing how fast the sensor can scan. So we'll see. We got a few more coming up here if they go through. But basically a wide variety of application materials can also be measured, not only the traditional metal materials, but also a lot of things like rubber, plastic, glass, mirrored surfaces, all sorts of things can be measured with a white light sensor like this. So we'll be going through those, and yeah, things like delicate glass, flexible plastics are no problem for a white light sensor like this. However, with a tactile probe, you'll see they can be a little bit of a problem in some cases. And obviously surfaces with special coatings can also be seen with a white light sensor like the dot scan. And there's many advantages, especially when it comes to reflective surfaces, transparent surfaces. All of those you may think with traditional optical sensors such as a camera, you won't be able to see a very reflective surface or a transparent surface very well. With a white light sensor, you can do this no problem. So the first little slide here, we're talking about traditional materials. Well, obviously with a sensor like this, you don't want to lose the ability to scan everything that you've been able to in the past. And with a white light sensor, no problem scanning traditional parts such as the one you see here in this little video. You can see it, the little white focal point is actually the point in which it's measuring, and it's scanning around those different contours and getting down into those smaller nooks and crannies. So things like metal parts are no problem with a CFS. Plastics, you'll see as we go through here, we'll show you a few more plastic parts. And then anodized surfaces, like I said, you have no problem seeing even very reflective surfaces. So, yeah, we'll let the video play out here. So when you see this sensor scanning like that, that's kind of a traditional way, and not too exciting, nothing too fancy going on. It's basically a little beam of light passing over a part, but it gets the job done. So, like I said, soft parts. This is kind of the big area where this part, or a white light sensor like this, really takes off, because with traditional scanning methods, if you have a part that's deforming while you're touching it with a tactile probe, well, that's no good. You're going to be altering your measured results in those cases. However, with a white light sensor like this, it's just a beam of light. There's no force exerted on the part, so you can measure soft parts like rubber, malleable plastics, thin-walled sheets, no problem with a white light sensor like this. Tactile probes, like I said, would cause deformation, and obviously tactile probes have kind of a diameter to the ruby, so you can't kind of get it down into all those small nooks and crannies. For instance, on the pictures on the left, if you had like a ring of sealant on a part like this, well, you could easily measure that with a tactile, or not, you couldn't measure it with a tactile probe, you could measure it with a CFS or the dot scan. So we have a little video here, but yeah, it doesn't look like the videos are going to go through at the moment, but we'll make sure they're available if you want to come back and rewatch them.
Charlie, you might be able to start them externally if you want,
sure,
like from the folder.
Yeah, let's try that.
I think there's some security issues possibly with PowerPoint.
Let's see. Yeah, it looks like I think the WebEx is blocking it at the moment. Are you able to see the video up there right now?
No.
No. So yeah, we'll skip the videos. If you can
part of
always
this
come
might
back.
be, I'm sorry, but you and
Go for it.
the two of you are in different places, and PowerPoint can create a barrier if you're not in the same station looking at the same information. And the only reason I know this is from delivering. So it might work for the first presenter, but not for the second presenter.
Sure, yeah. Okay, no, I get you. So, well, we'll keep going. You can always come back. We'll make them available if you want to rewatch them. So, also, reflective parts with a CFS sensor like this, no problem. You may think with a white light sensor where light's being shot at a part, reflectivity would be a pretty big issue. Well, you'll find as you measure more and more parts with this, it actually doesn't affect the results as much. There's no direct reflection, so you can get very high point rates. And you also don't need things like spray coatings like you sometimes traditionally do with other optical sensors. You need to spray down the part in order to have a surface that can actually kind of reflect back properly. Well, it's not needed with white light sensors like these. So things like mirrors, no problem. Chrome plated as well, no problem there. The nice thing about if you're measuring a chrome plated surface or a mirror is, well, obviously you don't want to touch that with a tactile probe. You're going to damage it, could scratch it. So a probe like this where it's contactless is very ideal for surfaces that are very delicate like those. Also, strong reflections on short chamfers. What we're saying by here is if you have kind of a very small, tight corner that you need to get into, well, with a tactile probe, you can't get down into those small corners. So with a very small sensor like this, where the focal point is extremely small, you can reach down into those small nooks and crannies, like I said earlier, no problem. All right, and then a big one is also transparent surfaces. So you may think, well, if you have a sheet of glass, the sensor is just going to pass right through, nothing's going to reflect back. Well, that's not the case. You do get some signal back that you can measure transparent surfaces like glasses and lenses. You saw a video earlier where it was measuring a lens kind of way back in the beginning. Brandon was talking about it. And you do get those focal points on not only the front side of the glass, but also the back side of the glass. You can do things like thickness measurements and find the thickness of a lens. Here on the picture on the left, you can see a brake light in which the focal point will focus on not only the front surface of that brake light, but it'll also go into the brake light, and you could analyze other peaks in your spectrometer in which, well, maybe the light's passing through the first surface because you want to measure the surface that's actually behind it, the back wall of the brake light. Where traditionally you'd have to take that part up, destroy it to get into the internals and measure the internals, and then you're kind of out a part. Well, with a white light sensor like this, you can measure surfaces through other surfaces, which is a very big benefit. Colored or transparent parts, like I said there. You can also measure the surface structure inside a part. So if you have things like air bubbles, well, obviously that's going to alter the way the light's reflecting back. So you will get some data regarding the makeup of a material, or if there's air pockets and things in there. Liqueur coating, basically that's what I was mentioning, where you can look through a surface down through into another surface. There's no really restrictions on what color a part is with a white light sensor like this. You can measure kind of the run of it. And one thing we mentioned here was, well, how do we measure the thickness of glass with a white light sensor like this? Well, we can see here in the diagram those the white light comes out of the sensor head right up here, and it hits the glass. So, and you not only have a focal point on the front of the glass here, but you have another one on the back side of the glass, right over here on the right side. And what happens is there is an indice of refraction right where that light is entering the glass. You do end up deflecting the light here a little bit. And so you do need to compensate for that by knowing what the indice of refraction is for that particular material. And what you end up seeing is you'll have two different peaks, and then you can, obviously, if you know the distance right here to the first peak, and you know the distance to the second peak, you then can find the thickness of a material, all from scanning it on one side. Traditional sensors, you'd have to go measure on this side, go around the material, and measure on the other side in order to get a thickness measurement like that. So it's a very added benefit because it speeds up your measuring process. All right. And then some interesting kind of fun applications here. We like to kind of push the boundaries of a sensor just to kind of see what it can do. So for instance, at one point we just scanned a quarter. Nice thing about sensors like this is you can take a lot of points in a very short amount of time, so you can kind of generate very accurate heat maps of parts. And so it's called CAD evaluation in Calypso, which is the software that the dot scan runs. And you can see there a nice little heat map kind of showing you where parts are good, where parts are bad. Obviously, if you have a part you don't really care to know, well, obviously you want to know if it's good or bad, but you need to know where it's bad or where it's good, so you can correct that in your process when you're manufacturing it. You can also do things like 4-axis scanning. You saw a video of it a little bit earlier where a part was in a rotary table, like you can see here on the left-hand side. Now you were looking at a smaller rotary table on the O-inspect, but this rotary table, what a rotary table does is it will spin a part. So not only is the part spinning in the 4th axis here, but your dot scan will move around the part and actually scan and scan the surfaces, all while the rotary table is spinning. So great for grabbing things like profiles, freeform surfaces. It gives you kind of a lot more options when you're trying to scan a complex part like a blade. And there's also different types of scanning modes with a sensor like this. Brandon hit on it a little bit, but one of the downsides with a sensor like this is you do have a pretty small measuring range to work with. And what that means is if you have a large defect in a part, well, obviously, if it falls below the measuring range, you're not going to get any light reflecting back up to the sensor because it's just going to be in thin air. The focal points will all be in thin air. So if there is no light reflecting back and up, you just won't get any signal and obviously no measured results on a part. Well, with guided scanning, what it does is it'll always have the sensor follow the contour of a part. So if the part has a defect and drops, the sensor will actually drop with the part so that it doesn't lose that data as it's scanning. And then here's kind of some specifications of a white light sensor. Now this is specifically for the dot scan, but other white light sensors tend to be pretty similar. The big ones here to kind of pay attention to are the measuring range. That's the width of the focal points of the different wavelengths. So from all the way from purple down to red, that's how much room you have to work with. So for a sensor up here, the 1 millimeter, you got about a millimeter. There are sensors that have increased measuring ranges up to 10 millimeters, and there are more that obviously go beyond that. The problem is the more and more you increase that range, the less and less accurate your sensor will become. So also another thing to kind of note is your working distance when you're using a white light sensor like this. The working distance is how far away from the sensor head, for like this area of the sensor, to where it's actually measuring the part. So basically, if you were measuring a part with the smaller 1 millimeter measuring range dot scan, you would have to be 10 millimeters from the part in order to have focus. Well, if you're trying to reach down into a deep borehole, obviously 10 millimeters isn't going to be far enough to reach all the way down to the bottom. You may need something like a 50 millimeter. But obviously, like I was saying earlier, the more and more you increase that, the less accurate it gets. So you have to kind of have a delicate balance of both. And then qualification, that's a pretty often or a pretty common question we get. People like to know, well, how accurate is a sensor? Obviously, the sensor is only as good as how accurate it can be. If you're familiar with tactile stylus, they're typically below 2 microns in accuracy. They can get down below much, even a lot farther than that, maybe even half a micron, depending on what type of machine you have and everything like that. And you can actually see these dot scans compare pretty similar. I mean, this one here is anywhere. The qualification sigma is kind of a good representation of accuracy. You can see it's anywhere from about a half a micron to 1 micron. And then the more you go up, the less accurate it gets. But I mean, you're still sitting here pretty good. 2 microns, 80 millionths for us Americans dealing with the English system. And spot diameter, we won't go through the rest of this here, but the big one, another limiting factor, is the angle range. So obviously with a sensor like this, you want to have perpendicular surfaces, or surfaces that are perpendicular to the sensor head itself. And when you get an angled surface, such as a 30-degree angled surface, obviously it affects the way the light reflects back. So you end up not being able to measure surfaces that are greater than 30 degrees plus or minus from that 90 perpendicular with a sensor like this. And obviously you can see here, the more and more measuring range you get, you lose more of that angle range, unfortunately. So it's kind of a delicate balance. All right, I'm almost to the end here, wrapping up kind of the future of white light sensor technology. Where is it going in the metrology industry? And then obviously we'll talk about kind of where it's going here at Zeiss a little bit. The big thing is application expansion. Like I was saying, this sensor can allow you to measure many kind of more non-traditional parts, such as rubbers, malleable plastics, very bright mirrored surfaces and things like that. Well, the industry is just wanting to expand its use more and more, give it a wider spectrum, so that in the long run, ideally this kind of a sensor would replace the old traditional tactile stylus, because it can really do everything a tactile stylus can't, and do a whole lot more, obviously. So it can do kind of both things. So it's definitely the way of the future. The one limiting factor is that angle range, because tactile stylus don't really have that requirement or that limitation, whereas a dot scan or a white light sensor does. So that's one thing we're working on here at Zeiss, is increasing the models of dot scans so that we can have wider angle ranges and obviously faster scanning. And the big one here is integration. We want to be able to allow this sensor to be put on any kind of machine, not just one type of machine that has a camera with it, like the O-Inspect. We want to be able to have it on all sorts of machines that are rotating, and that way you have the option to switch between a tactile stylus, because there are instances where a tactile stylus will be better. And we can also then switch over to a white light sensor like the dot scan in order to scan a part much faster if need be. So customization is always helpful. All righty, then some additional resources. This is where Brandon will take back over here.
Yeah, so we'll just go through some ways that you can get additional information on Zeiss products in particular if you're interested. So there's always our 1-800 number. If you call our 1-800 number listed there, you'll be connected with our Customer Interaction Center, where our colleagues can address your questions and direct you to the appropriate resource, whether that's an application engineer like myself or Charlie, or a sales representative, whoever it is you need to talk to. You can also feel free to email myself or Charlie if you have questions specific to the dot scan or Zeiss optical sensors. Another good place to find information on these sorts of things is the internet. So Zeiss.com/metrology is where you'd want to go for that, as well as the Zeiss Metrology portal. So on the Metrology portal, which you can find on our website, is it's basically a place where you can interact with other metrologists, other people in the industry, not necessarily Zeiss employees, but there's a forum where you can post questions and discuss various topics. We also have demo centers all over the U.S., so if you're interested in seeing one of our products, there's probably a location near you. And that's about it. So in this talk, we covered an introduction to white light confocal sensor technology, going through the theory and the technology involved in it. We also discussed the applications of the sensor, specific applications and demonstrations of the sensor's capabilities. And then we just gave you a brief overview of additional resources. And so with that, I think we're going to open it up to questions. So feel free to use the chat to ask us questions.
And I did see 2 questions in the Q&A box, so I don't know, is it Brandon that's manning the box? you might want to click on the Q&A as well.
I was, but I do not see any in the Q&A
Let me
box.
read the question. Maybe that's a good place to start. Isaac has written, so is this applicable in inspection of welds? Is the wavelength adjustable based on physical material thickness?
Is the wavelength adjustable?
And then a third question. Aside the angular measurement of not less than 30 degrees, are any limitations? If we could, please put the questions not in the chat, or not in the Q&A, but in the chat room, please. But do you want me to repeat these?
Yes, please.
Sure. So the first one is this applicable in the inspection of welds? The second is the wavelength adjustable based on physical material thickness? And thirdly, aside the angular measurements of not less than 30 degrees, are there any other limitations?
So I guess for the first one, I would say that, yes, it's a very versatile sensor and can be used for many different applications. So I don't see a reason why it couldn't be used for that. For the second question, I think it was whether or not the wavelength is adjustable. Yes. It is going to be a sort of a set range of wavelengths. It might not be exactly 700 to 400, but roughly that visible range is what it's going to function in. But depending on which sensor model, at least from a Zeiss perspective, depending on which sensor model, the different sensors have different measuring ranges. So if that's what the concern is, that you need sort of a larger measuring range, a different type of sensor will stretch out the wavelength range over a longer distance, which I think that might be where that person was going.
Okay.
And then remind me the third question.
Angular measurements of not less than 30 degrees was one limitation. Any others?
Yeah, I would say kind of the biggest one is probably your actual measuring range or your working distance. So for instance, if you had a very deep borehole that you needed to reach down into, well, this sensor only has so much reach. So you do kind of have to think about, well, what types of parts are you going to be measuring with a sensor like this? Can I actually physically reach the areas that I need to? So it's kind of, you do have to put some thought into it. It's just because there are that measuring reach limitation that you would have. And the other one then is, it is pretty good for like reflective surfaces and things like that, but it is always better to test it out. So that's why oftentimes if you were to get a sensor like this, it's always good to do a demo because you can actually see what your part kind of signal is reflecting back and everything, because you never really know until you try it with optical sensors like this. There's a whole lot of factors that can go into it, so it's always better to kind of test it out beforehand. But otherwise, I mean, really there is no limitations with kind of the number of points you can get. It's kind of however much your computer can handle. It's kind of the easy answer. And obviously you can't scan it too fast. You will, if you scan too fast, kind of lose bits and chunks of data. But I mean, 1,000 points a second, if you need more than that, there's other sensors out there that might do a little bit better of a job at gathering more of mass point data than like a white light sensor like this, where you're kind of looking at one individual little area. So, Brandon, if you have anything you can add to.
No, I think that covered it pretty well.
Isaac has a follow-up question to that, and it's, if it's as versatile as just said, does that mean it's portable, pocket-able kind of?
So I don't believe so. If I understand the question, so at least with the Zeiss dot scan, it's fixed on the CMM on the coordinate measuring machine, and that's to ensure accuracy for it. There are other types of optical sensors that are more portable, like laser line scanners that are handheld. Those types of things that would gather, as Charlie was saying earlier, like massive amounts of point data in sort of a portable handheld method. But for the Zeiss dot scan for white light sensors, that's typically not the application. That's typically not how they are used. not suitable for flexible plastics. I would say it is suitable
for.
Charlie, you want to take that one?
Yeah. I maybe misspoke, but this is the perfect sensor for flexible plastics. The one that's not are tactile stylus, where it's actually physically touching it with like a probe, where a ruby tip contacts the surface because that deforms it. Whereas with a white light sensor like these, that's ideal for flexible plastics because it's just a simple light shining on a part. It's not going to deflect or deform that material at all, just by light shining on it. So that's where this guy really kicks in. If you have parts that are flexible like rubbers, plastics, this guy's going to be your best bet to measure them. So sorry if I misspoke there.
All right. Last chance. Any other questions? And as Charlie and Brandon have said, that's their email, and that's an 800 number. So you're open to receiving communications after the webinar, correct?
Yep.
Correct. Feel free to reach out.
Feel free to email us. If you want to see any more videos or anything, by all means, shoot us an email. We'll definitely get those videos to you, so you can see them. They're a lot more of the videos are a lot more of the sensor kind of in action, so you can kind of see how it looks when it's scanning. So if that's something that you're interested in, just let us know, and we'll be more than happy to get those to you.
And as I mentioned, if you have any additional questions, please reach out to Charlie and Brandon. We will be sending out emails for the recertification units within 24 hours. It's an automated process. It checks whether you logged in and when you logged out, that sort of thing. And so we'd be looking for that, and we're going to use the email that you logged in with, you registered with. If that's it, I don't think we have any other questions. I'd like to thank both Charlie and Brandon very much for a very interesting and very high production value webinar. The quality of what you showed was very good. So I thank you very much. And
thank you.
And if that's it, then I'd like to end today's webinar. So on behalf of the Quality Management Division and the Inspection Division, we thank all the attendees, we thank the presenters, and everyone have a good day. Thank you.
Thank you, everyone.
Thank you.